And welcome to my series of short videos in which we discuss how the Arduino interacts with various electronic components. Yes, in less than 15 minutes we'll go over the basics, how they can be used, hints, tips, tricks and traps. And this week it's all about doing more than one thing with the Arduino. Just look at the board down here, my workbench, and you can see we've got two LEDs, right? One's flashing quite slowly, the red one, and the green one on the left is flashing at a frantic rate, yeah? Now, we're doing two things there, aren't we? And how do we do that? If you think you know how to do this, if you can do this on your Arduino, no fancy coding, no bit manipulation, just standard Arduino speak, C++, pause the video, have a go. If it takes you more than about 10 minutes, you obviously don't know how to do it and you can come back, all right? So I'm going to say goodbye now and see you in 10 minutes. Well, that wasn't 10 minutes, was it? Okay, let's just carry on. Now, the goal then is to flash these LEDs at independent rates. So let's wind the clock back and go really back to basics, because that's where this video is, of course, intended. It's intended for those programmers, those Arduino people who've got limited exposure to coding and possibly even the electronics that runs this, right? So let's go back to what everybody starts with, the blink sketch. I want to give a big shout out to PCBWay, PCB Prototype, the easy way. Now, we're all familiar with their special PCBs, $5 for 10 pieces, but you can also have Flex PCBs, advanced PCBs, and of course you can order custom parts. Let's have a look at the CNC and 3D printing options they have. So it's 3D printing first. You upload your CAD files as you would do normally for a PCB, but then you select your materials and submit a quote request. CNC machining is pretty similar in the way you submit your files, upload your CAD files, select one of these many different types of material you can use, and of course there are also 27 different options for the surface finishing. Just look at a few of those there, from anodized, brushed, bead blast, spray painting, and there's more under that list as well. And finally there's sheet metal, laser cutting and bending, so let's have a look at that. Once again, you upload your CAD files, select the product you want to make it from, and specify a few of the parameters here about whether you want threads, for example. And you can always submit your request for a quote, and it's about 7 to 9 business days to get it done. Okay, that's PCBWay. Excellent service, good quality. Why don't you check them out now? So this is where everybody starts from, yeah, me included. Umpteen years ago when I started with PIC programming, that's exactly what I did. And it's a good step to take, isn't it? You think, I've finally understood the connection between my computer, the Arduino board, or PIC board as it was then, and a bit of electronics and the code. And it's a good milestone. Unfortunately, the coding techniques in getting that single LED to blink are not the best. Let's have a look at the code. So this is, well, I made this up, but it's exactly the same as the blink sketch in the Arduino examples, right? Which everybody tells you to start with to make sure you know roughly what you're doing to upload a sketch to the Arduino. So what we do then, let's just whiz through this. We're defining one single pin, pin 10 here for our red LED, doing a bit of startup where we're saying the red LED is an output pin. We're setting it low initially because we don't want the LED to come on, do we? And that's all there is in the setup apart from this serial output. So you could, if you wanted to, trace it through. The blink sketch is simple enough. We don't need to trace anything with serial output. So we can just ignore that in here. Let's just close that up and have a look at the main loop then. So what we're doing in the main loop, we're saying for that digital write on the red LED pin, set it high. In other words, set the pin to 5 volts. And let the current flow. And we hang about for a bit, half a second in this case, and then we say now switch it off, and then hang about for a bit again. So it's an equal on-off situation we have here. You could change them, but that's basically it. Now you might say, well, what's the problem with that? I can do lots of stuff in my loop and stick delays in all over the place. Yes, you can, but your code will be, well, let's just call it suboptimal, because what's happening while this is going on, so the LED is on, you've just switched it on up here, you're now waiting for half a second. What else can happen in that half a second? What if a user presses a button, for example? A screen needs updating. anything basically. And the answer is tough luck. This is busy whizzing round doing absolutely nothing. So it's not the best way of doing multiple things on your Arduino. We're not talking about multitasking here, not really. It's all one big task because the Arduino is not sophisticated enough to have any kind of operating system with true tasks. But we can certainly emulate that, and it's the way your code should be written. So let's just move on to how we can get two LEDs blinking using the same sort of code structure as what we have here. So okay, we've got two LEDs now connected up to this Arduino, and we've said blink the red one and blink the green one. And I want the red one to be slow and the green one to be fast. Or it might be the other way around. Oh, that's not what's happening though, is it? Look, we get a red blink and then a very quick green blink and another red blink and then a very quick green blink. But hang on, the point here is we want them independently to flash. We don't want one to work and then another one to work. Yeah, we want them to run independently at different rates. So what's going on? Well, let's have a look at the code and see what the problem is. So as before, we define the LED pins. In this case, we've got them on pins 10 and 8. Yeah, we do the setup exactly the same as before. We set the output pins to output mode and set them low initially, and that's all there is in the setup. So let's just collapse that. Let's have a look at the loop now. So we've taken the code from the previous single LED sketch. We said, well, here's the red flash, and that worked well, so we'll stick it in here. And then we'll have the green LED flash underneath. Except, yeah, I know, you're ahead of me. You can see the problem. Whilst this is running, and, well, not doing anything in these delays, for example, this green LED hasn't even got a look in, has it? So it flashes the LED on the red side once. And then it comes down here and says, oh, now I've got to flash the green LED, only a bit quicker. And then it goes round the loop again. It goes, now I've got to flash the red LED for a bit longer time and the green one a little bit shorter. But they're not independent, are they? One is waiting on the other. The green bit of code here cannot run whilst this is running because it's all sequential. And we've got these big delays in where nothing can run. Isn't there a better way where we can say, don't delay, just do a bit, and then when you need to do a bit more, but don't wait. Yes, and this is what is called a state machine. Well, it's the first steps towards a state machine. Let's not get ahead of ourselves. You've heard the expression, walk before you can run. Well, we're going to crawl before we can walk, yeah, because you need to understand the fundamentals here before we start walking. So we've understood that this is never going to work because one bit of code is waiting on the previous bit of code to finish before it can work. And just to reinforce that message, let's have a look at that workbench again. So the red flashes, then the green, then the red flashes, then the green. That's not what we want. Okay. Lesson 1 then. How we can make that bit of code a bit more responsive and more to the point, independent. Red independent from the green and vice versa. Now this is looking a bit more like it. The LED on the right, the red one, is flashing at a modest pace, but the one on the left, the green one, is flashing like a thing berserk. And they're not interfering with each other. That's the whole point. Yeah, however slow the red one goes, it's not going to slow down the green one. And the green one is not waiting on the red one to do something and finish before it can get a look in. So how do we do this? Let's walk through the code. Okay, let's start at the top then. So, as before, we define what the output pins are, and they haven't changed. It's still 10 and 8. This is called forward declarations of our functions. You don't need to do that in the Arduino IDE because the Arduino IDE is caring, and it's for beginners to say, look, under normal circumstances, you would have to declare what functions there are on your program, but the Arduino preprocessor has a quick look for you and sticks them all in the front behind the scenes so you don't have to. Good. That's for beginners, that's very useful. But you don't have to do this if you're running this in the Arduino IDE. This is in fact a different one, so I do have to put these up here. The setup is exactly the same as it was last time. We're setting the output pins here for green and red and setting them low initially. That's all we need to say about that. Let's have a look at the loop then. Now the loop here, it's only 2 lines, and I'm saying blink the red LED and then blink the green LED. Now, does that mean go and blink the LED, let it blink, and then go and blink the green LED? Well, It can't do, can it? Because that's what we had in the previous example where the green LED was waiting on the red one to finish blinking before it got a look in. But here, as you saw on that desktop, we'll prove it again, nothing's waiting for anything here. So the loop is saying, go red, go green, and they're doing their things independently. How do we get to that stage? Let's have a look at the code after the loop in a bit more detail. So the code that the loop is now invoking to say go and blink the red LED is this bit here. Now let's talk about this in a little bit more detail. The very first thing we do when we come into the blink red LED function is to say take a snapshot of what the current milliseconds are since this whole Arduino turned itself on. All right, remember the Arduino can run for 49 days before that counter goes back to 0. So what we're saying is this variable here, red millis, is being set initially to the number of millis as it is right now. And then we're saying if the number of millis minus the red millis is greater than 500, do something. Well, it can't be greater than 500 the very first time because we've only just taken the millis into this variable. So it goes, well, no, that if statement is false. I'll just skip all that, go back to here and back to the loop. Off it goes. So it's done nothing. Think, okay, so back to the loop it goes. The loop says, oi, red LED, go. So back it comes into blink LED. Now this time, this variable is not affected. That is only done a first time because you've got this magic word at the front called static. What that does is ensure that this declaration, unsigned, long, red millis, is basically moved somewhere like here, in front of line 26 at compile time. But it also means that nothing else can update red millis. This the scope as it's called, where you can get red millis into your code, is only in this function. Now, I know that some people put things like this, they declare them like that up here in the main code, and they make them what's known as global. That's a very bad programming practice. After a few decades in the programming world, because that's my day job, I know about these things, and global variables are the Satan's spawn, believe me. Why are they global? Unless they are global for a reason, they most certainly should not be. And this red millis is only ever accessed here and here, nowhere else. So why are we making it global? We're not. We're going to keep it within the scope of this one function. But by putting that magic static word at the front, the compiler says, you want me to execute that statement the first time and then basically move this, as I said, in front of line 26 and keep it there as a sort of pseudo global, but not really. And that's the way to do it. And there's no if, buts or maybes. This is the way to do it. Now static, the keyword static in C++ does a multitude of things depending on where it's used. This is one use of it. So don't think this is the only use of it or where you read it again, that's what it's doing. It can have a lot of different types of meanings, which is a bit unfortunate, isn't it? But in this case, it just means only execute this line once when you first come across it and then move the variable outside of this function. Great. So the second time it comes in, then it's not going to execute this line here because it's already done it once. So we'll come into the if statement and say, well, is the number of millis minus the value we previously extracted from millis greater than 500? Now remember, we were just here probably less than a millisecond ago. If that loop is whizzing around a few thousand times a second, it could go, no, I haven't been running for more than a millisecond yet, go away. So it skips all the rest of the code and goes back to the loop. Yeah, I think you sort of start to grasp now what's going to happen, yeah, because eventually it will keep going around the loop and none of this coding is executed. And then suddenly, yes, half a second, 500 milliseconds has indeed passed since we took this snapshot up here of millis the very first time. And he goes, yes, we have gone beyond the 500 milliseconds. So now it says we're going to do something with that red LED. We're either going to turn it on or off, depending on what the current state of it is. So it says digital read, red LED, go and have a look to see what it is now. And that exclamation mark at the front of it says not, i.e. make this value the opposite of that value. So if this digital read was a low, it's going to make it a high. And if it was a high, it will make it a low. And that's what we're going to put into this statement here. So we're going to toggle it, flip-flop. Yeah, if it was high, we'll make it low. If it was low, we make it high. It's a nice little construct for flipping a GPIO pin. And then, of course, we must re-update that red millis value from the current value of the milliseconds. Because remember, 500 milliseconds at least has passed since we took the very first one up here. So we now update it, and off it goes out of this thing back to the loop. And the loop then eventually calls it again to say, okay, blink red LED, you're on. This line is not executed, remember, it's first time only. So it says, okay, is the millis minus the red millis that we updated down here, is it more now than 500? Well, of course it isn't. We've only just come from here less than a millisecond ago. So no, we skip. So the red LED is still on and will stay on however many times we come into here until 500 milliseconds has passed. At which point we do this whole thing again and go, okay, let's set the red LED, the GPIO pin for the red LED, to whatever it isn't at the moment. So we have a read and it goes, oh, it's on, it was high. And we're saying not with the exclamation mark, which is a low. So we're going to say digital write, red LED, low. That's what that will do. The second time around it comes in. We then capture the millis again into a local variable. And that's it. Back it goes to the loop. The loop will then say, oi, blink red LED, you're on, go. It'll come down here. It will not execute that line. It will come straight into the if statement and go, has it been 500 milliseconds since I was last here? And of course the answer is no. You've only just turned the LED off a millisecond ago. So it'll whiz round, keep getting called, keep getting called from the loop for half a second until eventually this condition is true. At which point it says, right, my turn to do something again. So it says, I'm going to set the red LED GPIO pin to, well, what are we going to read on the digital read red LED? Well, at the moment it's low. So it says not low, which is high. So we'll set it to high again. Red LED goes back on. And we snapshot the millis again in order to us so that we can have this 500 millisecond gap between each invocation of this bit of code. So as you can see, a lot of the time is just spent going from the loop to this function. The function says, no, this condition is not met on your bike. And it'll go back to the loop, at which point it gets immediately called again saying, blink red LED, go. And it goes, no, this condition still isn't met. It's only been 2 milliseconds. Back to the loop. And it will keep going backwards and forwards, backwards and forwards, backwards and forwards until it's met and half a second has gone past. Okay, so while it's doing all that, what else is it doing? Let's have a look at the next function down, which will look, funnily enough, very similar to this one. So the blink green LED function is identical to the blink red LED except for one little feature. This one, it said in the red LED, it says, has it been half a second since we did anything? In which case we either switch the red LED on or off. We switch it to whatever it isn't at the moment. But the green LED is only 100 milliseconds, so it's much quicker, well, 5 times as quick in effect. And you can tell that difference on the breadboard, can't you? It's flashing at a very fast rate indeed. So the loop, let's expand the loop again now here. The loop says blink the red LED, blink the green LED. And as we've just explained, when it calls this, most of the time it just exits immediately because this condition of has half a second passed is false. So it goes no, back. At which point the green LED function is invoked by the loop and go, well, green LED, have you got anything to do? And the green LED goes, no, I've got nothing to do either. It hasn't been 100 milliseconds because the Arduino is after all running at 16 megahertz, which means it's going to go around that loop several thousands of times a second depending on what code it's running in there. It's pretty fast. It can do a lot. But every 100 milliseconds it's going to flip whatever the green LED state is to either on or off by virtue of this statement. And every 500 milliseconds it's going to flip the red LED on or off. But the beauty is they're both being called and both being run several hundred times a second, and therefore the green LED and the red LED are no longer interfering with each other. So you think you've cracked the state machine now. Yay, we've done it. We've got a state machine and things can run no, it's not quite that easy. Yes, on this particular bit of code now, as we saw from the desktop, those two LEDs are indeed running independently. But that's only the very first step towards a true state machine, mainly because in that bit of code that you saw, there isn't actually a reference to a state, is there? We're just calling two functions here to say go, go. And the function itself says, do I actually want to do anything right now? No, I don't. Go back. Or, yes, I do. It's time for me to flip that LED on or off. But within the machine itself now, within this bit of code, there is no state. We don't know what the state of any of the LEDs are at any particular point in time. Yeah, we have no idea, which is why this is only the very first step towards a state machine. Now, the fact of the matter remains is that you might not need to go to a full state machine. And in fact, I'd say initially, don't. Why make it more complex than what you have to? We've got two LEDs running here. You could have 3 or 4 or 5, yes. Any number of functions that are called from the loop to say do this, do that, do the other. And each of those functions independently we go, is it actually time for me to do something? Look at the millis. Has enough time passed? No, it hasn't. Immediately exit to give another routine the chance. And if it is time, fine, then we'll action the code in that big if statement and go, yeah, I'll do this and I'll do that. I would say if you don't use this technique, now's your chance. Download the code. All the examples, all the stages of this particular demo are in the code, and you can copy one in after the other and just see how we progress from a blocking function that stops anything else running to this particular piece of code that allows this and many, many other things to run. I use this sort of technique all the time. Cool. I think we're done here. If you've got questions still on how this affects what your particular project's doing or how you can improve it, I might do a more advanced one into the state machine mechanism where we do have proper states within the machine to say, if it's this state, do this. If it's this state, do that. But it's still going to be based on this coding mechanism. So I do highly recommend you take it down and have a look and play with it. Become familiar with it, because this is most definitely the way to go. Cool. We're done here. Questions down below, as I've said. And if you think this was interesting and you've learned something maybe, give it a good thumbs up. And remember, there's plenty of other videos to choose. I'll see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.